Welcome back to the today's class. Today we will be seeing about AC circuit problems. An AC circuit consists of pure resistance of 10 ohm and is connected across an AC supply of 230 volt 50 Hz. Calculate the current, power consumed and equation for voltage and current. So this is the first problem. Here the given are the resistance value is 10 ohm and the supply voltage is 230 volt and the frequency of the AC supply is 50 Hz. Current I is equal to V divided by R. This is nothing but Ohm's law. So you know the voltage is 230 volt and the resistance is 10 ohm. So you will get a current of 23 amperes. To find the power consumed, you know the formula P is equal to V into I. Here, the voltage is 230 volt and the current consumption is 23 amperes. So, while multiplying this, you will get a power rating of 5290 watts. Now, the last part of the problem is you need to find the equation for voltage and current. So, to do this, we need to know the maximum voltage and the maximum current in the sinusoidal waveform. To find this, you need to find the Vm, that is the maximum voltage. To find the maximum voltage, we are having a formula root 2 into V. Here, the V is nothing but the given data, which is 230 volt. So root 2 into 230 volt will give you a voltage of 325.27 volt. Similarly, you need to find the current equation. So you need to find the maximum current. To find the maximum current, the formula is root 2 into I. Here root 2 into I give you the current rating, which is 23 amperes. So root 2 into 23, which will be equivalent to 32.52 amperes. So the last thing you need to find is the omega. So omega is equal to 2 pi f, and 2 pi and f is the frequency. So you put 50 Hz. Here pi is 3.142. So you can multiply this and you will get 314, that is 314 radians per second. So to write the equation of voltage and current, you know that V is equal to Vm sin omega t. So V is equal to Vm sin omega t. Here you have find Vm is equal to 325.27 volt, which can be substituted here, and sin omega t, here omega you have find it as 314 radians. So you can substitute this thing here. Similarly, the current equation I is equal to Im sin omega t. Im is 32.52 amperes and omega is 314 t. So this problem you have find the current, power consumed and equation for voltage and current. Second problem, three coils each having a resistance of 20 ohm and inductive reactance of 15 ohm are connected in star to a 400 volt 3-phase 50 Hz supply. Calculate the line current, power factor and power supplied. The given data are resistance is equal to 20 ohms, inductive reactance XL is equal to 15 ohms, and the line voltage is 400 volt. The resistance are connected in star. The supply configuration is 3-phase AC supply and the frequency is 50 Hz. These are all the given data from the problem. First, we are going to find the phase voltage. So here the line voltage VL is equal to root 3 V phase. So you need to cross multiply. V phase is equal to VL divided by root 3. Here VL is 400 volt. So 400 divided by root 3, will give you 231 volt. Next, you need to find the impedance per phase. So, Z phase is equal to square root of R square plus XL square. Here, the R square is 20 square plus XL square is 15 square. So, while simplifying, get 25 ohm. So, Z phase is equal to 25 ohms. Similarly, the phase current I phase is equal to V phase divided by Z phase. This is nothing but Ohm's law. I is equal to V by R. Here in AC circuit, the resistance is measured as impedance. So V phase divided by Z phase, which is nothing but voltage per phase divided by impedance per phase. Here the voltage per phase is 231 volt and the impedance per phase is 25 ohm. So you will get a phase current of 9.24 amperes. You know that the configuration is connected in star. So for star connected load, line current will be equivalent to phase current. So IL will be equivalent to I phase, which is equal to 9.24 amperes. So next we are going to find the power factor. Here the power factor is mentioned as cos pi, and cos pi is equal to resistance per phase divided by impedance per phase. Here the resistance per phase is 20 ohm divided by impedance per phase is 25 ohm. So you will get a power factor of 0.8 lagging. Here why lagging is represented? Because you can see in the question the resistance is 20 ohm and inductive reactance is 15 ohm. Since you are using coil, so the coil will have a inductance, and this inductance will give you a lagging power factor in nature. So you need to mention 0.8 lagging while calculating the power factor. Power supplied, this is the third part. Here you need to find power is equal to 3 VL IL cos pi. So 3 into 400 into 9.24 into 0.8. Here VL is the line voltage, which is 400 volt. Similarly, the line current is 9.24 and cos pi is 0.8. So you will get a power supplied is 5121 watt. Third problem, calculate the active and reactive component of current in each phase of a star connected 10,000 volt 3-phase generator supplying 50,000 kilowatt 5,000 kilowatt at 0.8 power factor. Find the new output if the current is maintained at the same value but the power factor is raised to 0.9 lagging. So the given data are the line voltage is 10,000 volt and the supply is 3-phase supply, and the power supplied to the load is 5,000 kilowatt and the power factor is 0.8 lagging. Here you need to find the current which is being absorbed by the load at 0.9 power factor lagging. First you need to find the power supplied. Here the power supplied formula P is equal to root 3 VL IL cos pi. Here the power supply is given, which is 5000 kilowatt. So here the line current is not given. So you can cross multiply IL and you can get the line current. IL is equal to P divided by root 3 VL cos pi. Here P is nothing but 5000 kilowatt, so 5000 into 10 power 3 watts divided by root 3 into VL is 10,000 volt and cos pi is 0.8 lagging. Now you will get the line current, which is 360.8 amperes. For star connected load, line current is equal to phase current. So IL will be equivalent to I phase, which is nothing but 360.8 amperes. Next, we are going to find the active component of current which is flowing in the load. To do that, you need to multiply I phase into cos pi. So here you know the I phase, which is equivalent to IL. So 360 into 0.8 into power factor is 0.8, which is equivalent to 288.64 amperes. So the active RMS current flowing in the circuit is 288.64 amperes. So the reactive component. To find the reactive component, you need to multiply the phase current with sin pi. Here you know the I phase is 360.8, but you don't know the sin pi value. To find the sin pi value, you need to do a simple calculation. Here pi is equal to cos inverse of 0.8. Here you know cos pi is 0.8. So now you are going to find pi. So pi is equal to cos inverse of 0.8 will give you a value of 0.6435. So the pi value is 0.6435. To find sin pi, you need to substitute sine of 0.6435, which will give you sin pi is equal to 0.6. So you can substitute 0.6 over here, and while multiplying this you will get 216.48 amperes. So the power output, that is the last end of the question, you need to find the power output when power factor is raised to 0.8 lagging, 0.9 lagging. So the power output P is equal to root 3 VL IL cos pi. So root 3 is same, VL is 10,000 volt and the line voltage is 360.8 amperes and the power factor is 0.9. Here you need to use the new power factor to determine the power output value. You should not use the power factor which is given to find the other parameters of the system. So the new power factor value is 0.9. So your power output is 5624 kilowatt. Fourth problem, a 3-phase 440 volt 50 Hz delta connected motor on full load has an efficiency of 90%. A input power is 16.67 kilowatt and power factor is 0.82 lagging. Find the line current. The cost of running the motor for 10 hours, then the price of 1 kilowatt hour being 80 pice. So in this problem you are going to find the line current and the total amount of rupees you need to give to the power supplier. So the given data are the supply is 3-phase and the line voltage is 440 volt and the frequency is 50 Hz and efficiency of the motor is 90% and the power input to the motor is 16.67 kilowatt and the power factor is 0.82 lagging. And another one thing to notice, the supply configuration is connected in delta. Power supplied P is equal to root 3 VL IL cos pi. So you need to find the line current, which is IL. So you can cross multiply. IL is equal to P divided by root 3 VL cos pi. You can substitute all the values and you can find the line current is 26.67 amperes. Next, you need to find the energy consumption, which is the second part, the cost of running the motor for 10 hours. To do this, you need to find the energy consumption in running the motor for 10 hours. So, the input power, that is Pi, is equal to 16.67 kilowatt. So for 10 hours you need to multiply 10 with it. So you will get 166.7 kilowatt hour. So the total energy consumed by the motor by running for 10 hours is 166.7 kilowatt hour. Similarly, the energy charges, you can see here the price of 1 kilowatt hour is being 80 pice. So for 166.78 kilowatt hour you need to multiply 0.8. So 166.7 into 0.8 will give you 133.36 rupees. So if the motor is being run for 10 hours, then you need to pay 133.36 rupees as energy charges. 340 ohm non-inductive resistances are connected in delta across 400 volt three-phase line. Calculate the power taken from the mains. The resistance is 40 ohm and the voltage phase is 400 volt and the supply is three-phase and the frequency of the supply is 50 Hz. If it is not mentioned, assume the frequency as 50 Hz for all problems. For delta connected load, phase voltage will be equivalent to line voltage. For star connected load, phase current will be equivalent to line current. So the only difference is for delta connected load, the phase voltages will be equivalent to the line voltages, which is V phase is equal to VL, which is equal to 400 volt. Next, the phase current I phase is equal to V phase divided by R. Here, the phase voltage is 400 volt and the resistance is 40 ohms. So, you will get a phase current of 10 amperes. For a line current, the line current will be root 3 times of phase current. Here, root 3 into 10 amps, which will give you 17.32 amperes. Similarly, the power supplied P is equal to root 3 VL IL cos pi. Here root 3 into voltage, that is the line voltage, is 400 volt and the line current is 17.32 and the power factor is 1. Why the power factor is 1 here is, you can see it is a non-inductive resistance load. So if it is a non-inductive resistance load, then it will be a pure resistance will be present in the load. So for a pure resistance, the phase voltage and the phase current will be in phase. So the power factor will be unity. Power supplied by the mains for delta load is 12,000 watts. Three similar resistors are connected in star across 400 volt three-phase supply. The line current is 5 amperes. Calculate the value of each resistance. To what value should the line voltage be changed to obtain the same line current with the resistors connected in delta? So you are going to find the change in current from star to delta connection. The given data are the line voltage is 400 volt and it is a 3-phase AC supply and the line current is 5 amperes. So for star connection, you know that the phase voltage will be equivalent to line voltage divided by root 3. So 400 divided by root 3 will give you 231 volt. Similarly, for star connection, line voltage will be equivalent to phase voltage, so it will be equivalent to 5 amperes. Resistance per phase will be equivalent to voltage per phase divided by current per phase. Here, the voltage per phase is 231 volt divided by current per phase is 5 amperes. So the total resistance per phase is 46.2 watts. For delta connection, line current is 5 amperes. It is given in the question. So to what value should the line voltage be changed to obtain the same line current with the resistors connected in delta? Here the line current is same, that is 5 amperes is same. Then what you need to find here is how much amount of voltage should be adjusted in delta so that the line current should be 5 amperes. So line current, that is the IL is 5 ampere, is given in the question. Here you know that phase current will be equivalent to IL divided by root 3. So 5 divided by root 3 is 2.88 amperes. And the voltage V phase is equivalent to I phase into R phase, which will be equivalent to 2.88 into 46.2, which will give you a phase voltage of 133 volt. The phase voltage of delta connected load is adjusted to 133 volt to achieve the same line current of 5 amperes. So to get the same line current of 5 amperes in delta connected load, you need to adjust phase voltage to 133 volt. Thank you.